Okay, so get back to Unit 8. So we're talking about neural networks now. I think it's a pretty exciting point in the semester. So we have the demo in this unit is sort of a simple toy demo where we have a data set that has green points in the middle, blue points on the outside. It's not linearly separable. We learned that in the last unit with SVMs, we learned that it's possible to do some sort of transformation, usually to a higher dimensional space, where maybe we can make things linearly separable. And in the last unit, we talked about doing that with kernel functions and the kernel trick, but we only had a list of predetermined kernels to choose from, and we don't really know whether that's going to work in any particular data set. So what we're saying in this point, in this unit, is to say, let's actually learn a transformation for our data set that's going to be custom to it, and therefore we don't have to worry about choosing the wrong kernel and all that. And so that's the main idea, and that's the idea that's powering this revolution of deep networks and so on that's changing everything. So so we're going to learn about that, just at least from the simplest setting in this unit. So so the approach that we're going to use to tackle this is one of many different ways you could tackle this problem, but this is a pretty common one. So it's a two-stage approach. In the first stage, we're going to learn four, we'll call them transformed features. You could say that these are going to be like our v of x. And the particular features we're going to construct here, each one of them is going to be the soft output of a linear classifier. So what we mean by soft output is just that the output has been mapped to the interval from 0 to 1, which is sort of like saying it's a probability, as opposed to being a score, which is a real number from -infinity to infinity. And we know one way to do that is if you have a real number and you put it through a sigmoid. Actually, sigmoid would be like this. If you put a real number through a sigmoid, it maps it from 0 to 1. Okay, so that's how we can do that. And then we're going to take those four outputs, and we're going to treat that as our new feature vector, phi of z, and we'll just do standard linear classification. In this case, we're going to do just binary logistic regression. Okay, so essentially what's happening here, the features we learn, because we're building them with linear classifiers, we know how to think about that. Each linear classifier, we can imagine that it has a decision boundary. And so let's say, let's take this blue classifier here. So depending on how the weights are constructed, one of these sides will give us scores that are positive. The other will be scores that are negative. Turns out for the weights that were learned here, positive scores are going to be this way. And so if this is a positive score and we put it through a sigmoid, then we're going to get a soft probability that's greater than 0.5. So maybe so over here, this is going to be, if you go far to the left here, it's going to be approximately 1. And if you go far to the right here, it's going to be approximately 0, because the sigmoid kind of tails off. And we can do this and actually here is the picture. This is showing the value of this number versus x0 and x1. So you can see here, when the value is 0.5, that will happen right on the boundary. And as you go to the left, value gets closer to 1. As you go to the right, value gets closer to 0. Okay. And then we're doing the same thing for each of these. So this next one, you can see that as you go in this direction, it's a 1. This direction, it's a 0. This line, this direction, it's a 1. And then This one over here, it's a 1 in that direction. Okay, so perhaps what you can see is happening is that it's trying to isolate this region here, which is in the intersection of all those half spaces. Right? So we can think of like all the points to the left of this boundary, that's a half space. Or let's say the points to the right would be a half space. The points to the below the green is a half space, and so on. And if we take the intersection of those 4 half spaces, we get this shape, which is approximately where the green points are. Okay. It's a little bit more complicated than that because these are all going to be like soft boundaries. It's not a hard boundary that goes from 0 to 1. It's more like it gradually changes. And so, but anyway, what the second stage is going to do is it's going to try to recognize when points are in this half space, or sorry, this intersection of half spaces. And it's going to do that by linearly combining the 4 numbers, these 4 numbers. So can you see what the weights will need to be for the second stage, roughly speaking? So what will the signs of the 4 weights need to be from these pictures? Does that sound like I'm asking something crazy? All negative?
Yeah.
Okay. So, well, what about this one?
I guess I didn't know how we were defining the signs on every boundary condition.
Well, so the picture tells you here. So when you're dark red, that's positive. That's closer to 1, right? And when you're light red, that's closer to 0. So essentially, we want to reward when you're below this line because that's where we want, right? But then we want to reward the opposite for those 3. Okay, so, and actually we're printing the weights here. So when you look at the weights, this is negative, negative, positive, negative. So the weights that we learned for the second stage are lining up with our expectations. Yeah, and then this is just showing what's plotted here. And so finally, when you put that all together, so you take these numbers, these 4 numbers, and you scale them by those 4 weights and add it all together, you get this picture. We call these heat maps. So this heat map, which shows that you get numbers close to 1 when you're in this region and numbers close to 0 when you're out here. And of course, there's a transition as you softly go from output of 0 to output of 1. So somewhere in here, there's a 0.5 that you could use as a threshold to get a hard classification of 1 or 0. And you can see it's doing a pretty good job. Okay, so it's really important to understand what's happening. Are there any questions? I know sometimes, yeah.
So initially, just deciding kind of where those boundary lines are going, can you just explain briefly that process or what?
Great question. It's learned. So we're not telling it to put the lines there. All we're really telling it structurally is use 4 linear classifiers. So that kind of implies that there will be 4 lines somewhere, determined by the weight and the bias of each one of them. But we are using the approaches that we've developed until now, maximum likelihood training with some data set, to learn all the weights. There's some details because it's a trickier problem because it's not a linear function of all the weights anymore because of these nonlinearities we stuck in there. But we'll talk at the end of this unit about how to go through all the tricky calculus to figure out the gradient, to run gradient descent. But that's how we're going to do it. So yeah, these weights were learned. We didn't tell them to put them there. If you run this again, you can run the demo yourselves. If you run it again, it will choose a different initialization, random initialization, and you'll get slightly different lines. Maybe they'll be like this or whatever. It's different every time, but you'll see, pretty similar behavior.
So we're talking about the number of parameters for this. Like each one would have, say, two for like where that gradient is, right? And then one for the weight. So like each one would have, say, 3 parameters, and you combine all those.
So how many parameters do I need for each of the lines?
2.
2. So that would be 8. And then
You need 1 for each weight, right?
and then the final layer has how many? There's
4.
and 1 bias.
Okay, and the bias, yeah.
Yes.
Okay.
So a total of 8 plus 4 plus 1. So 13 parameters in this case. Yep. Yeah. So these are great questions. Any other questions? Yes.
Why do you need 2 parameters per line?
Well, in linear regression, you know, it's all about placing the line, and you have
Oh,
basically
yeah.
an intercept and slope.
Okay.
Do we use 4 lines for any specific reasons, or can we use?
Another great question. So, would it work if we had 3 lines? I mean, you would maybe have something that's a little bit more crude, but I think it would work if you had 2 lines. No, 2 lines wouldn't work, right? Because I can't really place 2 lines in any way, because I would get some region like this, and it would get all these points wrong and all these points wrong. So that's a great thought experiment. It's basically asking, like, what's the dimensionality that I need for this problem of my new transform features? And so we see that 2 is too few, but 3 should work. 4 works. What happens if I have 5? What's going to be different? Will it work better?
May or may not.
May or may not. Yeah, exactly. So why might it work better? Why might it not work better?
You have more opportunity for discrimination between the
Yeah.
different data sets.
It's true. Yeah. So when if I have a whole bunch of lines and I can like very precisely craft
Overfitting?
a shape.
Same
Exactly. Right. So we have like a bias variance trade-off. So as I have more and more lines, I could eventually get like, you know, a very creative boundary that, you know, it could I mean it's not perfectly flexible, but you can imagine that with more lines I can more carefully shape a boundary. But then the problem is I have a limited training data set, and so I have the problem of overfitting and having variance too high for the size of the data set that I have. So yeah, so these are all things you have to consider when you design a neural network. One of the most important considerations would be to choose how many of these transform features you have. And that's like, so on the final project, you'll be doing this stuff with just some data set, some real data set. You won't know what it is. You'll just need to try, you know, maybe a grid search over different numbers of features, try different choices and see what happens. See what the best option is using cross-validation. Okay, good. Any other questions? So is it making sense, this overall? Okay, so so let's look at it from some different perspectives. So this would be like a block diagram notation that I think is very familiar for electrical engineers. So here we have our 2 inputs coming in. We're going to put those x, we're going to multiply them by a matrix and then add a vector. So this is a linear transform. This, when you add something to a linear transform, technically you can call that an affine linear transform because of that added parameter. But people usually just refer to this as a linear stage instead of affine linear. But this is also, you know, hopefully familiar to what we've seen in classification. So here's our scores, and then we put each one through a sigmoid, and then we get these probabilities, if you want to think of them as soft outputs. And then this last part is once again going through another linear classifier to get the output score. And as we'll discuss, you can optionally put it through a sigmoid to turn this into a probability between 0 and 1. Or if you wanted, you could just leave it at that. And as long as you know how to interpret it, you know, you would say anytime this is positive, that determines the inner region, and when it's negative, it's the outer region. But in any way, I mean, for the demo code, we did implement this in part to draw this picture, this is the output picture, which is scaled from 0 to 1. So we wanted the final output to be in that range. So this part here, we call this stuff the hidden layer, and then this other stuff here we call the output layer. And so for the hidden layer, we use these H's everywhere. So these are the hidden layer scores, hidden layer weights, hidden layer biases. This is the dimension of our hidden layer. These things, these soft outputs or activations, these are our hidden layer activations. This H will be our sigmoid function. And then for the output, the output layer as input takes the hidden layer activations, then applies some output weights, output bias, gets output scores, then can put that through another sigmoid to get an output activation, and so on. So that's just a new notation here, hidden layer, output layer, H's and O's. And so the interpretation of this overall network is really just logistic regression. Because we can think of everything from this hidden layer is really just implementing a feature transform, right? This is just transforming our features X to these new features, A in this case. I'll write that. So this is going to be equals our hidden. So these are our hidden features. And then at that point, this is just exactly linear regression. And linear regression, and we're going to train it using logistic regression, train these, which is, as we know, connected to the sigmoid. So overall, we're just doing logistic regression with a particular choice of a feature transformation. And what's different is we're learning, what are the parameters here that we need to learn?
The W's and the B's.
The W's, B's, exactly, all these. We need to just learn those to minimize our logistic regression loss, right? Binary cross entropy. So in principle, it's stuff that we've done. The only thing new, as we'll see, is like how do we compute the gradients with respect to these things that are deep in the network. It's kind of a pain because they go through these nonlinearities and so on. But we'll learn how to do that with something called backpropagation. Yeah.
Would there be an issue with removing the sigmoid activation in there? With
These ones?
yeah,
Great question. Let's consider them gone for a moment. So what remains, how could we describe all of that? Is that linear? Affine linear, the function taking here to here. Is that going to be linear when these are gone? So it's like we have W0 output transpose WHX plus BH plus B0. Okay. So I can rewrite this as W0 transpose WHX plus, and then a new bias term, which is W0 BH plus B0. Actually, this last one is just scalar. Okay, so here, this is our new, this is just a new weight vector. This is a new bias term. So it is linear. It is affine linear. So once you take this out, you have just a complicated way to implement an inner product with a new vector and an offset with a new scalar.
so you basically be just one layer. Then.
Yes, you're back to logistic regression, which as we know is not very sophisticated.
Yeah.
It's not very awesome. You would fail on this data set because this data set is far from linearly separable.
So that kind of decoupling allows us to get more use out of.
Yeah, these nonlinearities are kind of everything. You take the nonlinearities out, then it just collapses to, unit 5. So when you put those in, it's really this thing that works in a fundamentally different way that can all of a sudden do nonlinear classification with like a nonlinear boundary. So yeah, it's super important to have these. Yeah, that's a great question. Okay, any other questions so far? All right. So let's talk a little bit in more just mathematically about training. So we said that these are the parameters. Let's just, for notational purposes, just collect them all into a vector theta, so we can, we can expand this into a vector and concatenate with all this other stuff, and now theta is a vector, and we just say, how do we train theta? Well, like always, we have our training data, x, y pairs, n of them. Because essentially we're saying we're doing logistic regression, we know that the likelihood function, probability that the output label equals 1, given the input xi and our parameters, just has this form. This is the logistic sigmoid. Now, this is going to be the output score for the ith label, since we're talking about the ith train label. But this score here is some complicated function of the original input xi and all the parameters theta. Right, so this whole thing here is like f. So it involves all these parameters in a complicated way. But, we can just notationally say that all that's this big F. And at that point, it looks very familiar. Instead of this being a linear function of x, this is now a nonlinear function of x, but otherwise it's still logistic regression. And we still have the same likelihood as always. And that's nice because we know exactly how to deal with that likelihood. So we can just return to, this is the maximum likelihood procedure that we learned back in, I think, unit 4. And then we plug in the negative log likelihood, which in unit 5 we derived for this guy has exactly this form when the labels are 0 and 1, and called this binary cross entropy loss. So everything is good. We now, based on unit 6, we know that we can do this minimization iteratively by running gradient descent. We derived, in fact, in that case for the linear f, we derived a way to compute the gradients. And now we're going to have to learn a new way because it's a bit more complicated. But in principle, it's going to be building on tools that we've learned, in particular the multivariate chain rule. So these are kind of all the things we've learned. We're just putting them together. And this is the new part. Okay, any questions on this? Okay, so we'll get back to training a little bit later. But let's pause to ask a few questions. So why is this thing called a neural network? Well, it turns out when you look at biological neurons, they work in a similar sort of way. So this would be like a biological neuron here, and it has a bunch of these things here. I think these are called the synapses, or maybe these are the dendrites. Okay, so these things act to collect charge from other neurons like this one that's coming in. And once the charge accumulates and is large enough, then this will send out a signal. So we can think about that through this simple mathematical model. So these things are like the input charges coming in from different directions. And then this has learned to weight them each by a certain amount. And then they just get summed together, so that's the accumulated charge. And then when it's greater than a threshold, that's what this is showing. This is, you could say, like our logistic sigmoid is giving some sort of approximation of that. When that exceeds a threshold, it sends out a signal. So this would be one stage in our neural network, and it's like one neuron within a larger brain or neural system. So basically that similarity is why we call these neural networks. Any questions on this? All right, so a little bit of history then. So this model that we just discussed here was proposed in the 40s at least, and this guy Donald Hebb, he kind of proposed all these theories about how that works and how that works for learning. Like when you have many of these things connected together, how do they interact, and how does it eventually learn something that we know? So that's this neural plasticity stuff. And then in the 50s, people started playing with these ideas from the perspective of artificial neural networks, not the biological ones. Though of course biological research continues, but so this guy Rosenblatt basically proposed this idea as a way of learning something, and this is a single neural network, and now we know that that's really essentially what logistic regression is, right? When you do this with a sigmoid function, that is exactly logistic regression, and he proposed something like that and called it the perceptron back then. There were some early computer implementations, and in these days, computers probably use tubes. And so as you can imagine, they were pretty limited in terms of their power. But as we know, linear classifiers themselves are pretty limited as to what they can do. So for all those reasons, it didn't go very far. In the 60s, people pushed it a little further. They said, well, what if you have multiple stages of these neurons, similar to this? What's an organized computational framework to compute all these gradients and so on? And they figured out what's called backpropagation, which we'll talk about later. But still, because of all the hardware limitations and so on, it didn't go very far. So then there was sort of a second wave of this in the 90s, where we had a lot more computational power. We had more data sets and all that. And there was a huge resurgence of this stuff in the 90s. But then it kind of died out. It seemed like it kind of hit its peak. It wasn't really saturated. Didn't really go anywhere. And so in the early 2000s, if you were working on neural networks, you were not cool. You were stuck in the past. You were laughed at. But then there were a few brave, persistent people that kept working on this over all those decades, 2000s, 2000, and so on. And eventually, things caught up, and they had enough computational power. They had big enough data sets, and they were able to outperform all the other state-of-the-art techniques. First, this happened in speech and in image processing in 2012. And then it was just like dominoes, just other fields one by one took over. And so now we're in the middle of this revolution. You could say it's like third wave of AI. So there was this initial wave, and then there's a second wave, and now this is the third wave. So, but we'll talk about these deep networks in the next unit, Unit 9. So just sort of a high-level overview. Yeah.
When we were starting the image classifier, you mentioned that the U.S. Postal Service was trying to develop the handwriting. When did that kind of fall into this?
I think it was like late 80s, maybe 90s. It was kind of like in this sort of wave. Yeah. Yep. Okay, so all right, so let's get into just a few more details now. So this is a very strange diagram for an engineer, because, or at least for an electrical engineer, I don't know about other engineers, but for electrical engineers, we always think of the circles or boxes as the systems and the arrows or lines as the signals. And so here it's actually the opposite. So the circles are the signals. So these would be like your input features, and these are your hidden features. So let me put, this is like your x vector would be those three things. And then your hidden coefficients, your AH vector, would be those things. And the stuff that happens in taking you from x to AH, that is denoted by the arrows. So this is the equation that we saw a couple pages ago. This is now written, for specific hidden index L. You take all your input features, you do this inner product with your hidden weights, you add your hidden bias, you put it through a sigmoid or some other nonlinear function. It doesn't have to be a sigmoid, but it has to be nonlinear. And then you get this. Okay, so this is actually how a lot of the computer science people draw the diagrams. So it's a little bit weird at first, but then if you think, okay, this is a computer science person, then it starts to make sense. So even some of these other ones we saw, like even this one, as you can see, circling the signals, and then the weights are along the arrows. Right. So anyway, so now that you can recognize this, you can interpret it. Okay, so I think we talked about most of this before. DH is the number of hidden units. These are things we need to choose. Activations, this is the particular type of nonlinearity, something that we can choose. We'll talk about this in a moment. In the output layer, here is this is our affine linear transform, our linear weights, bias, and then this is another activation function that's happening over here, but this is optional to use it, and I'll explain what I mean by that. But you don't have a lot of choice. If you decide to use it, you have to choose it well, otherwise it just doesn't make sense. So we'll talk about that in a moment. But anyway, so when you see networks of this form, they're most often called multi-layer perceptrons. So that's kind of the buzzword, or MLP. MLPs is what we're studying in this unit. MLPs could have 2 layers like this, or they could have more than 2 layers. When they have more than 2 layers, you can call them a deep network. They can have, in some cases, hundreds or thousands of layers, although there are some challenges with that. But in this unit, we're going to focus on 2 layers because there's just a lot of basic stuff we need to learn first. And once we learn it for 2 layers, it's just a lot easier to learn it for 2 layers. And then in the next unit, we'll talk about what happens when you have more than 2 and all the new issues you have to face and struggle with. Okay. All right. Any questions so far? All right. So moving on to, so here I wrote everything with summations and indices, but for me, it's a lot easier to write things with vectors and matrices. It just looks a lot cleaner. So here's the block diagram. Again, linear transform, matrix multiply, add this vector, and so on. When you write this step, where you go from the scores to the activations, often people write it like this. So these activations for the hidden layers, they always act element-wise. So this is, in other words, this is a function h that's taking a vector and returning a vector, but it's just operating individually on each element alone. Okay. More generally, there would be some big operation that would mix all these together, but that's not happening here. These activations, they're made simply. You really don't need, the nonlinearity being in there is crucial, but people don't usually come up with some big, crazy nonlinear function there that involves multiple inputs and outputs. Just simple little scalar nonlinearities. Okay, the output layer is very similar. So I think in this case, previously we just had one output node, but now, in general, we can have more than one. In this case, I happen to have 2. And it turns out that the output activation could be a function that actually does involve everything. It's not necessarily element-wise. As you can see, this is a little picture of the 2 dimensions here. If one dimension goes this way and the other dimension goes this way, you can see that both of them are used together to get the value of the activation. And so one place that you have seen this is the multinomial logistic, the softmax. That function, if you remember, that was like e to the minus zk over sum over L1 plus e to the minus ZL, if I remember this right. So as you can see, this function takes in a whole bunch of different z's, like in this case 2, and depending on the output index, so k would be like this would be k equals 1 or k equals 2, it's going to act differently. But in both cases, it involves all of the inputs. So, and actually I plotted, this is what's plotted here. These are little softmax functions. Okay, so these guys act element-wise, but this output activation, again, it's optional, but it, in some cases, acts on the full vector. Especially if you're doing classification of more than 2 classes, then you're going to typically have a softmax here, and the number of classes you have will determine the number of outputs you have. Just like in multinomial logistic regression. All right, any questions on this? Okay, moving forward. So let's talk about the activation layer now. Hidden layer activation function, little h. So the one we've been talking about is the sigmoid. As we know from chapter 5, it takes this form. This is what we, back in that chapter, this is what we called the probability that y equals 1 given z. Z being the linear score. It's a mapping from the real line to the interval between 0 and 1. So it starts from 0, goes to 1, like this. So a few things to note about it, kind of qualitative things. The output is bounded, so it can never go beyond 1 or below 0, but it's not centered. So meaning on average, let's say if your inputs are centered, so on average your inputs are around 0, then your outputs will be centered around 0.5. And so that might not be what you want. If you always want that for every layer going to the next, things are 0 mean, then this could cause problems because it immediately makes the next layer non-zero mean. So if that's what you want, there's a very simple fix. It turns out that the hyperbolic tangent is exactly the sigmoid that's centered vertically. So if you multiply the sigmoid times 2 so that it goes from 0 up to 2, and then you subtract 1, then the sigmoid basically goes from -1 to 1, and that's the hyperbolic tangent. So you could stick this in place of the sigmoid, and it probably wouldn't work all that much differently. And as you can see, it's very, very similar in spirit. And actually, it works a little bit better for a somewhat convoluted reason, because in general, when you train this is a non-convex optimization in those parameters. So it means you can get stuck in local minima. And typically, you start with a random initialization, and there's a particular way to initialize people have worked out that works pretty well, where these guys are initialized randomly according to particular distributions. And those distributions get kind of messed up when the outputs here are non-zero mean. So it likes those to be zero mean. So for that reason, this tends to work a bit better than this when all things are considered in terms of not falling into local minima. Okay, but there are other options. So a very simple and popular option is this rectified linear units. And so this is a function that is 0 whenever the input is negative, or if the input is positive, it just copies the input directly. So basically, we can write it like this. You take the max of either 0 or your input, and you report that as the output. So qualitatively, this output is unbounded. In other words, as your input gets larger and larger, the output gets larger and larger. It's not centered. But when we talk about deep networks, this is by far the most popular choice for reasons why we will discuss. And if you use them in shallow networks, actually they work pretty well there also. So the point here is that there's a lot of options. These are probably the most common ones that people talk about, especially for multi-layer perceptrons. And yeah, they all have like pluses and minuses about them.
I know we had talked about with other machine learning methods that differentiability would basically help you converge
Yes.
faster. Does that occur here? Because I mean, like the regular, I mean,
It's
looks
not
simple,
differentiable, yeah,
but
yeah.
it's much faster to compute, right? Because you're just taking a max.
Yeah, that's a good question. So it turns out that in practice, this does not seem to impact the convergence rate. So I think if you had like, so I think with these neural networks, there's much bigger problems to worry about. It's like you have all these bad local minima. You need to somehow like jump out of them and jump into good ones. And so for all those reasons, you can't use a very large learning rate step size. You need to keep it small. And so when it's small enough, like the non-differentiability of this point doesn't really affect you that much. So yeah, in the end, it's maybe a little counterintuitive, but yes, it's not something people talk about very much. Although there are alternatives to this. So there's like a version which does something like where it just kind of smooths this out. And it's the SILU. I'm trying to remember what it stands for. Sigmoid linear unit. And this one seems to do a little better, maybe train a little faster. So yeah, maybe there is something to it. But this is really kind of the workhorse that sort of the default people tend to use. All right, good. So now let's talk about the output layer activation. So we have to now talk about the task we're interested in solving. So let's say we're solving a binary classification problem. And so in that case, we want that our output is just a scalar. As we saw with logistic regression, for the binary case, we just want one output. And there's two options here. Option one is not to use any output activation function. So we just output Z0, or sorry, ZO. This is basically the score, right? We output the score directly, and that's enough because we know that if we have a positive score, that essentially means that the label y hat, we say the label y hat is 1. And if it's negative, we say it's -1. So that's enough to make a decision. It's also enough to train the system because with how we formulated training before, let's come back to here. So in fact, this is the expression we derived to train the logistic regression. And it's actually written in terms of the linear score z. So that's actually enough for training as well. So that's one option, is just instead of having this last stage in your network, just get rid of it. Just have your network end there. It's not the only option. The other option is, as we did before, to put your score through this logistic sigmoid and output this thing. As we know, this thing is now sort of like a probability. It's between 0 and 1. And there is another way, we'll see it, there's another way to train this where you write the likelihood in terms of this quantity, not z. And so, the details of the gradient will be a little different, but it's another possibility. So you really have these two options. But for binary classification, these are really the two main things people use. They don't use too many other things in these. In 99.9% of the cases, you'll do one of these two things. Now, if you're doing multi-class classification, that would be where you have more than two classes. Then the way we think about it is we one-hot code the class. So if we have k different classes, or one-hot code the targets, so we make a vector of k entries, and when the jth element is large, then we think that x came from the jth class. This is essentially how we've always done this. So here again, we have two options. Option one is just to have the neural network output the score vector alone and stop there. And if we do that, we already derived the expression for how we train it and everything. That was the multinomial logistic regression. We're done. But there is another option. Option 2 is you put that through the softmax function. Oh, actually, I think I drew it. I wrote it down wrong over here. So this should not have had this here. Okay, so that's the softmax. And if you do that, that's fine too. Now there's going to be a different expression for the likelihood function that involves this, but it's a known expression and you can work with it. So those are the two options there. Again, there's not really too many other options that make sense or are used in practice. Finally, if we're doing regression, not classification, so we're just trying to predict some real number, or let's say we can generalize this to predicting k real numbers simultaneously. So k could be 1 or more than 1. Then, essentially what everyone does is just have no output activation at all, just output the z vector itself. In fact, if you do something like you put it through a function like this, you're actually changing the output significantly, right? You're taking a real number and you're squashing it into the 0 to 1 interval, and all of a sudden it looks totally different. It's probably nothing like what you were trying to predict. In fact, if you were trying to predict something that goes negative once in a while and you put it through this, you could never predict it when it's negative. So generally speaking, you don't want to do any processing at the output of your network. You just output ZO, and that's it. Okay, so again, output layer activation, in order to choose it, you have to think, what task am I doing? Is it binary classification, multi-class, or regression? And then you have some options in each case. Whereas for the hidden layer activation, you have a lot of options. You can use any of these for any task. It's really just, you have to try them to see which one works better. You don't know for a particular data set until you try them. Okay, so those are the activation functions. Any questions on any of them? Okay. Now, let's finally get to the loss functions. So here again, we have to consider what task we're solving of these three. So let's say, for the moment, binary classification. So we said one option there was to have our network output ZO. And in that case, we know that we can write the likelihood, or let's say, the likelihood, we write it like this. This is the logistic sigmoid. And then we can basically turn this into this expression. So our likelihood over all of our training samples takes this form. So when we take the negative log likelihood, which is what we usually work with, we did a derivation that showed us we get this. And this is in the case of 0, 1, yi, and we call this binary cross entropy. Now, as I mentioned before, we have another option, which is to put that ZO through the logistic sigmoid. Let's call it AO now. Now this AO, this is in the interval between 0 and 1. And this guy has a new log likelihood. This log likelihood is actually a little bit more structured. You have the label yi times log of AO plus 1 minus yi times the log of 1 minus AO. And this is actually a quantity from information theory called the cross entropy. And this is where we get that name. This is the cross entropy between Y and A. Okay, so this is why it has that weird name. It's really this form. So here, it's important that if you build your network to output Z, you have to use this log likelihood. On the other hand, if you build your network to output A, you have to use this one. If you use the wrong one and you train it, it just won't work well. So it has to be matched. Any questions on this? Okay. So next thing is, what if we're doing multi-class classification? So this is more than 2 classes. So now one option is we build a network that outputs ZO, and then we derived this likelihood here that involved something we called the softmax, and we constrained that. We look at the negative log likelihood. I think we derived an expression for that. Oh yeah, it's right here. This is the negative log likelihood expression. We just minimize this using gradient descent. We call this the cross entropy. The meaning for why we call this cross entropy is not clear until we consider this other option where our network actually includes the softmax and outputs this AO, which is going to be a vector of values. So if we have k classes, this is going to be a vector with k entries. And then in that case, when we build our negative log likelihood, we use this expression. And once again, this term is the cross entropy between y and the A vector. So that is where this term comes from. Okay, so once again, how you build your network, whether it outputs Z or A, determines how you choose your loss for training. They have to be matched. Last case is regression with k-dimensional targets. So here we said we're always just going to output the last linear stage. That's just going to be our output, what comes out of that. The most common assumption is to build a likelihood that says that the targets, y, are a version of your output that is corrupted by additive white Gaussian noise. And in that case, we derived, basically we saw this first in Unit 2, then later on in Unit 4. The negative log likelihood of this is just our quadratic loss. And so essentially we're doing something like least squares, except it's a nonlinear least squares because this z is nonlinearly related to our original x. There are other options. As we saw in the midterm, if instead you assume that the additive noise is Laplacian, then the likelihood ends up being an absolute value here, and that gives you L1 loss. That is another popular option, especially for image processing, but it has there's other reasons why. It turns out that when a few of your samples, your z's, are very far off from the y's, you can think of them as outliers. They just don't fit the model at all. This model will perform very poorly. It will get really confused by the outliers. It'll pay a lot of attention, too much attention to those outliers. If you instead assume Laplacian noise, it doesn't care about the outliers as much because its model, its tails shrink at a slower rate. So it basically says, you know what, those outliers I'm used to them. I'm not going to pay too much attention to them. And it can do much better. And so essentially it says, instead of using L2, you use L1. In some cases, that's going to work a lot better. So, but we'll focus on just this quadratic loss, I think, in almost all cases for this semester for regression. Okay. All right, so good. So it's good stopping point for today. So we'll talk next time about training. But for now, I think that's enough. Have a good weekend. See you guys on Monday.